Right, so now for number 7, we have done an athlete on a horizontal athletic field throws a discus. The height of the discus above the field in meters, careful, that's our units, after it is thrown can be modeled using a quadratic function of the form blah blah blah. Okay, this is a general form of the quadratic function. It's, how it comes. So x represents the horizontal distance, so x is going to be horizontal distance that the discus has traveled from the athlete. A specialized camera tracks the initial path of the discus after it is thrown by the athlete, and the camera records that the discus travels through 3 different points. And those 3 different points are here, and are here. As shown in diagram 1, they are there, and they are there, and they are here. All right, cool. And so for part A, we need to use the coordinates of this first point, the one that I have in green, okay, the one that I have in green, to write down an equation in terms of A, B, and C. So guys, just so that we understand, when they say in terms of A, B, and C, it means that you need to have an equation with those variables inside of it, okay? And so you might have like a number equals blah, 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 A, B, C, okay? This is the main idea. You have equals A, B, C. All right. When they talk about, I don't know, y in terms of x, you want to have y equals blah, 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 x. All right. In terms of A, B, C, you want to have equals A, B, C. All right. So that's the first intuition I'm going to share. And the second thing I'm going to talk about is, all right, so this point that I have in green, this one here, all right, it belongs to what type of function? Ah, they first told me that we're talking about a quadratic function, so I can use this equation here. This equation here is technically also in your formula booklet. If you look up the whole thing about slopes and axis of symmetry, here it is as well. Okay, so if you ever forget it, but you identify the buzzword quadratic function, here it is in your formula booklet. Back to the test. So my general form, okay, is f of x equals ax squared plus bx plus c. And so this green point that we talked about earlier is 3 comma 2.82. 3 comma 2.82. And so if you go ahead and plug in this point into the quadratic function, well, let's remember that this 3 is x and this 2.82 is y. And let's remember that f of x is the same as saying that this whole thing is y, okay? And so that whole thing is y. That means you will be having 2.82 equals ax being 3 squared plus b times 3 plus c. And if you simplify this just a little bit, you're going to end up with 2.82 equals 3.39a plus 3b plus c. And so this is for the green point, okay? All right, so that is for part A. Then part B, which is way more points, asks us to use the answer in part A and two similar equations, okay, similar equations, to find the equation of the quadratic model for the height of the discus. Now you guys, this is a classic, okay? Think about it this way. To build a quadratic function, you need 3 different points. Okay, that is the main idea that we're going to draw from this exercise. To build a quadratic function, you need 3 different points. You need 3 different points because, as you can see here, you have 3 different variables. Your variables being A, B, and C. Okay, once you discover A, B, and C, well, I mean, technically your variables X and Y, but once you discover A, B, and C, you can plug it in and end up with a quadratic function. So for a quadratic function, you need 3 different points. For a line, as you can see here, you have two things you need to discover. You need to discover M and you need to discover B. So for a line, you only need 2 points because there's 2 things you have to discover. For a quadratic function, you need 3 because there's 3 things you need to discover. And lo and behold, they give us 3 points. And so the version in green is right there. The point that is in blue, I'm going to do it now. So the point in blue is 6, 4.25. So here we're going to be plugging in 6, 4.25. And so if I go ahead and plug in 6, 4.25, you end up with 4.25 equals a times 6 squared plus b times 6 plus c. So 4.25 equals 36a plus 6b plus c. So this is the blue point, all right? And last but not least, we have the red point. The red point is 9, 5.30. So 9, 5.30. So if you plug that in, you're going to end up with 5.30 equals a times 9 squared plus b times 9 plus c. You do a little bit of quick maths, and you're going to find that 9 squared is 81. So 81a plus 9b plus c. Okay, this is a b. Looked like a 96 for a second. This is a b. Okay, yeah. So here I have my 3 fancy equations. Okay, and just to be like a little more organized, okay, I'm gonna write them all down like on top of each other. See, so here I'm gonna have the 2.82 equals 9a plus 3b plus c. Here I'm gonna have the 4.25 equals 36a plus 6b plus c. And at the bottom, I'm going to have 5.30 equals 81a plus 9b plus c. All right, you guys. So from here, if you think about it this way, you have 3 equations and you have 3 things to discover. That means you can discover it, okay? And if you discover a value for a, b, and c, you're going to be able to plug into this guy here, and boom, you're going to have the equation of a quadratic model, okay? So as long as you find a, b, and c, you're good to go. Now, from here, technically, if I get very mathy and fancy with you, this is a system of equations. When you have a system of equations, you have to play around with them to get a, b, and c. Now, you have 2 main tools, you guys. You have the first tool called substitution, and you have the second tool called elimination. All right, I think this video would be insanely long if I show both. So to my liking, I feel like substitution is a little more friendly, okay? But if you see a way to do it with elimination, you do you, all right? So the whole point of substitution and elimination is that you decrease, and this is the key idea, you decrease the number of variables, okay? So notice right now I have, we're gonna call this my first equation, this one our second, this one our third. And so in our starting point, you guys, help me see, in our starting point, how many variables do you have? In our starting point for all 3 of these, you have A, B, C. So you have 3 variables, okay? Well, I'm not going to put in parentheses because it might be a little bit weird, but you have 3 variables, all right? You have 3 variables in your starting point. But the moment you use substitution or elimination, you're going to see we go from 3 to 2. And that is the magic of system of equations. That is the cool thing about it, if there's anything cool about math. So, for example, this first one, what we can do is that I can end up with c equals something, okay? So let's say that c on this first one, right? Let me rewrite the first one. So the first one is 2.82 equals 9a plus 3b plus C. So if you want to get C alone, you're going to have to do minus 3B minus 3B. That's 2.82 minus 3B plus 9A equals, oh shoot, my bad. So 282 minus 3B equals 9A plus C. And so from here you can do minus 9A minus 9A. Clearly you end up with a C that is alone. So you end up with C equals 2.82 minus 3B minus 9A. And so this right here, I'm going to call it 1 with an asterisk. Okay? This is all just so my process is a little more organized. Okay, this is not like how you're supposed to do it or whatever. No, this is so that your procedure is more organized. It's my way to do it. I put numbers to each of my equations, and if I change one around, I put an asterisk next to it. And so number 1 asterisk gives me that C is this whole thing. Okay, so now I take 1 asterisk and I plug it into the second one or the third one. I'm just going to choose arbitrarily to plug it into the second one. So the first one with asterisk is going to enter the second one. So if I do that, I end up with 4.25 equals 36A plus 6B plus C. But C, ladies and gentlemen, is now this. This is C. Okay, so that means I have plus 2.82 minus 3B minus 9A. Now, hold up. Let's take a breather. Notice, this is a very long equation. This probably looks a little bit scary. But, key idea pulling through. Originally, we had 3 variables. How many variables do you have now? Ah, you only have A and B. So we just passed from 3 variables to 2 variables. Okay, and how did we do that? Through substitution or elimination, in this case, substitution. And so the whole magic of substitution and elimination is that it helps you decrease the number of variables. And eventually, we're going to reach only one variable. So we're going to reach A equals, I don't know, 9, okay? Or B equals 7, because you only have one variable. We're not quite there yet, but we're almost there. So if I combine some of these like terms, I can have this 36 with this, this 36A with this 9A, right? So that means I have 27A plus this 6B with this minus 3B plus 3B plus 2.82, right? And so from here you choose to get either B alone or A alone. I'm going to choose to get B alone. So I'm going to do minus 2.82 to both sides. Bada bim, bada boom. That is a decimal that no one wants to calculate. So I'm going to pull up my graphing calculator. There it is. So my graphing calculator, trusty rusty calculator, I'm going to do 4.25 minus the 2.82. Bada bim, bada boom. 1.43. So 1.43 equals 27A plus 3B. To keep getting B alone, you got to do minus 27A because there's a plus next to it. So that means that 3B equals 1.43 minus 27A. And now if you go ahead and divide by 3 because you want to get B alone, you got to divide everything by 3, right? Golden rule of algebra, something we've learned over these last 2 years of IB, hopefully. B equals 1.43 divided by 3, whatever that is. Okay, so 0.476. Now, if you want to do this in significant figures, or actually, yeah, so significant figures, you would count 1, 2, 3. Do you round it up or keep it the same? You round it up. So we're going to leave it as 0.477. All right. Minus 27 divided by 3, I'm pretty sure is 9. But we all double check sometimes. 9. So 9A. All right. So from here, we just found that B equals 0.477 minus 9A. I'm going to call this 2 asterisk, okay? And so now with 2 asterisk, I'm going to plug it into number 3. So 2 asterisk is going to enter the third one that is untouched, okay? So the third one untouched is 5.30. Oh, wait, actually, give me a second. Give me a second. So this is my value for B. This is my value for B. Right, so if I go ahead and take this one, so now the weird step that I just recalled, okay? So notice how on the one hand you have C equals something, and on the other hand you have B equals something, right? So if you go ahead and plug both of these things into like any equation, right? Let's say the third one, see? So I'm gonna go ahead and put like all into the third one, see? So you do all into the third one, you're gonna end up with 5.30 equals 81A. So I'm talking about this one here, right? 81A plus 9B. Now we did say that B was 0.477 minus 9A, right? And then you're going to have the plus C. But you know that C from here has to be, plus C is going to be 2.82 minus 3B minus 9A. But you know that B has to be this guy. And so, right on that step, you're going to say that it's going to be minus 3 times 0.477 minus 9A. Minus 9A. See? So let's take a moment to really understand what just happened. This is your C. This C that is here, right? And so, and this right here is your B, which is what we plugged in for this, okay? So now, this is an even bigger equation. It looks even scarier, but how many variables do you have? Will you look at that? You only have A's going around. So yes, it looks scary, but now you have one variable, which is A. And that is happiness for a system of equations. See? So notice how the procedure is always the same. You're going to take, I don't know, what I suggest, right? Put numbers to each equation. You're going to take, I don't know, the first one and leave it in C equals terms of B and A, right? So here you have C equals something something B, something something A, all right? Later on, you're going to end up with B equals something something A. And so that means that you can plug both of these things in such a manner that you end up with only A's. Okay, that's the whole idea. You end up with only A's. All right? This is a procedure that you can practice a lot. There's a couple different ways to do it. This is just the one that I suggest. All right? If you see a shortcut, find a shortcut, do your thing. But a procedure that might take a little bit longer but always works is this one. Okay? Anyways, from now we need to get A alone, which is of course terribly annoying. But once you find A, everything else just kind of flows. So for 3 points, I feel this exercise is pretty long. But it's surefire points that maybe take a little bit longer, but you're going to get all 3. Because the procedure is very mechanical. It's always the same thing. So 5.30 equals this 81A that we talked about, plus 9 times this. So 9 times this is 9 times 0.477, 4.293, 4.293 minus 9 times 9A, it's going to give you 81A, plus 2.82 minus 3 times this, so that's going to be 3 times 0.477, 1.43, 1.431, sorry, and times negative 3 times negative 9. So that's going to be plus 27a. And then we have the minus 9a at the very end. All right. So from here, a couple things you can do. This goes away with this. And let's say I combine all of these, right? So you're gonna, when you combine all of these, you do 4.293 plus 2.82 minus 1.431. So that means on the right side, you're gonna end up with, I mean, you still have 5.30 on the left side. On the right side, you end up with 5.682 plus whatever is the remainder of these two a's, right? So 27a minus 9a, I'm pretty sure it's 18a, but I'm gonna double check because that's how I am. It's 18a. And now you just need to find the value of a. And so to get a alone, you do minus 5.682 minus 5.682. You end up with 18a equals that. So 5.30 minus 5.682, boom. Negative 0.382. Negative 0.382. If you go ahead and divide by 18 to both sides, you're going to find that a equals, finally, you're going to have that a equals 0.021 negative. So negative 0.021111. If you do significant figures, however, you skip the zeros and you count 1, 2, 3. Round it up or keep it the same, you keep it the same. So significant figures, we're going to leave it as negative 0.0211. So this, ladies and gentlemen, is my value for A. And yes, you might be thinking, all right, oof, finally, so much work and we got a value for A. Well, yeah, now you got to find B and C. And so some of you are probably thinking, dude, I thought we were done. What the heck? And no, we're not done, but everything that's coming is very easy. Okay? Once you find one of the variables, whether it's A, B, or C, it just kind of flows, dude. I'm just saying. For example, here, you have an equation that is B in terms of A. And so if you plug in A, you're going to get B. So if you plug in B into, I mean, if you plug in A into this one, right? So you're going to be putting this there, right? You can see that B has to be, that sounded funny. B has to be 0.477 minus 9 times negative 0.0211. So that means that B is 0.6669. So B equals 0.6669. Now, if you do significant figures, you're going to count 1, 2, 3. Do you round it up or down? You round it up. So B is going to be, wow, wow, wow. B is going to be 0.667. All right. And now, as you can see, we got a value for B incredibly fast. And with these two values, now it's super easy to get C. You can even plug it into one of these and you're going to get C. But just to be a little bit more rigorous, we're going to plug it into this one here. Okay? So if you plug it into this one here, you're going to say that 2.82 minus 3B, and we know that B is 0.667, right? Minus 9A, and we know that A is negative 0.0211. You end up with a value of C of 1.0089. So C equals 1.0089. And if you count three significant figures, you go 1, 2, 3. You do count the zeros because they are after an actual number. Okay? You do count the zeros because they're after an actual number. So 1.00. Do you round it up or keep it the same? You round it up. So significant figures would be C equals 1.0. You guessed it. 1.01. Kablam! And so here are my values of A, B, and C. Now we can plug it into this guy here. And that means that the whole thing for part B just ends up being f of x equals your A, which we said was negative 0.0211 x squared plus 0.667x plus 1.01. If you're asking what did I plug into, we plugged into the quadratic function, which is this guy here, okay? And again, we know that it's this because of this here and because of the buzzword quadratic function, okay? So that is for part B. A little bit long, but a procedure that is always the same. And so from in that sense, this exercise is a little bit friendly, all right? Anyways, that is for part B. Then they tell you that a 1.8 meter high wall is 30 meters from where the athlete threw the discus as shown in diagram 2. And we need to show that the model predicts that the discus will go over the wall. And so from here, you can just say, look at the diagram, it's going to go over the wall. And you're done. Just kidding. I wish it was like that. For part C, we have to do a little bit of critical thinking. And so this f of x, right? This f of x, blah, 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 this one here, right? Let's recall that f of x is the same as y, okay? And so that means if you do a little bit of a table, if you plug in x, you get a value for y. And so this is going to give you a bunch of different points, right? In fact, if you plug in 3, for example, you're going to get 2.82. If you plug in 6, you're going to get 4.25. And so you're going to get all those different sets of points. If you plug in 9, you're going to get 5.30. Okay, why am I saying that? Because you know that the distance from 0 to the wall is 30 meters. And so which x value does this wall have? This wall has an x value of 30. So here, you know that you have an x of 30, but you don't know the height, okay? Now the height you would be finding is the height of the discus. So you're going to be finding out just how above the wall the discus is flying, right? And if you happened to get a value that is below the wall, then you would say, okay, it's going to crash into the wall, all right? Pretty straightforward, not that complicated. Identify that you need to plug in 30 for x and compare it to the 1.8 meters of height, all right? So if our y value is bigger than 1.8, it's going to fly right over. If it's lower than 1.8, it's going to hit the wall. If it's at 1.8, it's going to hit the wall at the very top, okay? So go ahead, take your calculator, and we're going to be plugging 30 for x, okay? So you plug in 30 for x, so negative 0.0211, 30 squared. We double check that it's correct. It looks fine by me. Plus 0.667 times 30 plus 1.01. And so here we see that you get a value of 2.03. And so 2.03, I mean, the height here at 30 is 2.03. And just so we understand what I mean by this, it's the point that it's in red. Okay, so the discus is going to be at 2.03. And is this above the wall? Well, how tall is the wall? The wall is 1.8 meters high. And so for part C, you're just going to say, oh, at f of 30, we got 2.03. And 2.03 is higher than 1.8, the height of the wall. And so this is the way that you show that the discus will go over the wall. And so writing this is good enough, but if you want to like whatever be more rigorous, you can also literally say hence or therefore the discus shall go over the obstacle. All right, just kidding. Say it as you want, but you can say therefore the discus will go over the wall. All right, that is how the answer key leaves it. All right. And I want to point something out that's very important, that is a test taking strategy, which goes beyond number 7. It goes about how to approach these exercises. So the day of the test, you might be reading, or let's say the day of the test you face this problem, okay? So you face this problem, you say, okay, part A is worth 1 point, and it's pretty easy because you write just one equation. Part B, as we saw, takes way longer. Okay, you identify that it's about finding the equation of a quadratic model. You know you can do it, but you know you take a long time, right? And so maybe it's not the ideal to do it right away, but notice part C was just plugging in 30, and it took me probably like 30 seconds. I mean, I spent some time explaining it, but the day of the test, you're gonna say, plug in 30, bada bing, bada boom, 2.03. It would have been way faster. See, this video is longer because I'm explaining everything, but the day of the test, it would have been pretty fast. And it's some pretty fast 3 points. And so this is something you have to consider, right? Yes, part B takes a long time. And yes, it's maybe not worth the points for the amount of time it takes. But part C is super fast. And part C is worth 3. And you can't do part C without part B. And so really, like, if I were to make this like more fair in terms of grading, I would probably say that part B is worth like 5. And I would make part C worth 1. Because in terms of time, that is a better reflection of how this score should be done, in my opinion. Okay? Point is, you read this and you say, okay, part B takes a long time, part C is super fast, and so if I do part B, part C is going to net me a lot of points. And so this sort of analysis can help you identify which exercise you do first, which exercise you do second. Always do what you feel comfortable with first. This is not just a test of your math skills, this is a test of your test taking skills. It's a test with time, okay? You don't have all day to do it. Um, might as well prioritize the stuff you know first and whatever nets you the most points first. All right, so just keep in mind what I just said. It might help you down the road. Last but not least, for part D, we need to find the horizontal distance that the discus will travel from the athlete until it first hits the ground, according to this model. And so basically, looking at this diagram here, it's all right. So we're talking about it hits the ground, so we're talking about this point here. All right. And so essentially from here, you need to find what they call, because this is an XY, you need to find what they call a x-intercept. All right. And so there's a couple different ways to find the x-intercept, but the main idea that we need to immediately understand is that an x-intercept is x, I mean it's something, comma 0. For a y-intercept, it's 0, comma something. All right. So on the one hand, what you can do is that you take your equation and you equal it to 0. So you're gonna have 0 equals, because your y is 0, right? So 0 equals negative 0.0211 x squared plus 0.667 x plus 1.01. All right. And from here, you have a couple of tools. All right. You can do the famous maybe factoring, although factoring here seems incredibly hard. You can do factoring. You can use the quadratic function. All right. B squared minus 4ac divided by 2a, which, by the way, let me just check if it's in the formula booklet. And you have graphing, okay? For today or for this one, I'm gonna probably just do graphing. Let me look at the formula booklet to see if the quadratic function is here. Quadratic function, zeros maybe. I don't think it's here actually. Probably would have showed up. Anyways, so it's not even here. See, this one, I don't think it's in the formula booklet. I don't recall it at least. Point is, this one helps you find the x-intercepts, all right? And so you literally plug in A, B, and C, and it helps you find the x-intercepts, all right? You've probably seen that in class, so I'm not going to go over it now. The most efficient way, in my opinion, to do this is just to graph it. So go to y equals and put this whole thing. So negative 0.0211 x squared plus 0.667x plus 1.01. Now, guys, a lot of you might be thinking, dude, every time I do graphing, like, my window is always, like, so messed up, and I just don't know what's going on. I don't like graphing because I can't get the right window. Guys, it's not incredibly hard, okay? A lot of times by context, you can get a better window, all right? So this is a quick 101 on how to get a good window on your graph so you can use all the functions you need, okay? and find all the intersects and all the good stuff. See, the first step you're going to do is, well, of course, plug in your equation into your y equals. The second thing you're going to do is you're going to press zoom and go to what is called zoom fit. Okay, zoom fit is especially good for finding intersects. Okay, here we're trying to find a zero. Okay, so it's an x-intercept. Zoom fit might not get that, but zoom fit is really good if you're trying to find an intersect of like two lines. Okay, so anyways, I can put zoom fit, and from here I don't see the x-intercept. You're correct, but I get a better idea of what my window is looking at. Okay, and so now you could go to window and change what you need to change. Now, first things first, by context, the window, um, by context, you can figure out what your window should be. All right. So first things first, they talk about this wall, right? That is 30 meters, right? So I mean, sorry, at 30 meters, you have this wall. So at an x of 30, you have this wall, and the discus goes over the wall, and so your window should probably be like around here, right? This should be your window. And so an x of maybe 50 would make sense, right? So just by context, it makes a little bit more sense. Your x minimum should be 0 because you only care from where the athlete throws the disc, okay? Now, thankfully, zoom fit helped me put x at 0. But if it didn't, now you know. See, you only care about positive values. Y minimum, well, it puts it at 1.01 because that is your y-intercept. But I'm going to put it at 0 just that it looks pretty. And your Y max, well, the 6 looked fine. It looked like where the maximum was. But just to make it look pretty, I'll put 10. See? So notice, I know some of you might be thinking, dude, you're just like pulling these numbers like whatever from wherever, right? And I'm saying no. I look at the context and I put a bigger value. Okay, that is another hint I'm going to give you for a nice window. Put values that are overly big. Okay, if you want to have a perfect graph, I would probably put an x max of, I don't know, like 40. But I just want to see the intercepts. I just want to see where it crosses lines. Put a number that's a little bit bigger. See? So now you graph it, and yes, it's a little bit bigger. Yes, maybe it's not as pretty, but you see everything you need to see, right? I'd rather have my graph look like this than be fighting to have the exact value and stuff like that, and then, oh, like my x is there, but barely. I don't know. I'd rather have you go overboard and calibrate from there. Okay, that is my main message. Go overboard, calibrate from there. And so from here, I can do second calc, find a 0. It literally says 0. Whenever you use the 0 function, it's just for finding the x-intercepts. Okay? And so the 0 functions for x-intercepts. Here it asks for left bound. So I'm going to put that around there. And then it asks for right bound. I'm going to make sure it's way to the right of my x-intercept. And now you can guess, right? Let's just understand what I just did. So when you do the left bound and the right bound, which I did like somewhere here and here, right? Notice the little arrows at the top of my graph, the same arrows I'm drawing here. What you're asking your calculator is, okay, this is my left, this is my right. Scan in this area. Find all the zeros you can, and with the guess function, you pick your 0. Now in this case, there was only one 0, so the guess function is going to give you the only 0 that there is. But it's not guessing because your calculator is dumb. It's guessing like, okay, pick the 0 you want. But in this case, with the bounds I chose, there's only one 0, and there it is. It's at x equals 33.05. And so, if you get very rigorous in this approach, you would say that the horizontal distance is going to be 33.0. 33.05. All right? And so technically, well, because we use significant figures, our answer is a little bit different from the mark scheme. But as long as you're consistent, you're going to get full credit. I want to point something out just so that you know. Remember how I equaled it to 0? Okay, this is a key idea. And this actually gives you one method point. And the other point is an answer point. All right? So be very careful. This whole idea of equaling to 0, I know that I said it for us to understand that, oh, it's an x-intercept, right? And so you want to equal it to 0. But it gives you a method point. So write it out, okay? Part of part of writing it out is that you're telling the guy grading, I know what I'm doing, okay? And even if you don't know what you're doing, it's a method point, so do it, okay? Might as well write it. It's going to get you a method point, and that is, ladies and gentlemen, for number 7. And just to clarify, if you look at the answer key, you're going to see over here that our answer was a little bit different, right? And part of this is because there's a lot of different ways we could have gotten our answer for our quadratic, right? You could have done it like us, doing the significant figures, or you could have put in like the whole entire values, or you could have been one of those weird guys that does fractions, okay? I'm a weird guy too, don't feel offended. I also like fractions, but I do it in decimals because, most people prefer decimals. Anyways, um, point is, because this one has like the ultra mega specific decimal range, okay, this one is more accurate, right? It doesn't mean that your other answer is wrong using the significant values. I mean, yeah, with the significant values, but you're going to be off by a little bit, right? And so the answer key, yes, it has it at 33.0. We got 33.05, but really, because we followed our method, because we followed our answer from before, you're going to be okay, all right? I'm just saying, if you're looking at the answer key and you're freaking out because you're off by a little bit, you're off by a little bit because the significant values make it a little less accurate, okay? But that's fine. As long as you're consistent, you're going to get full credit. Trust me on that. Don't worry. For part D, the answer was 33.05 meters. Make sure you showed your method point as well by equaling to 20 because it's an x-intercept. All right, guys, that is enough blah blah by me, and that is number 7.